Alright, so in this unusual democracy where everyone is not equal, the vote count is a function of worth of the voter. If rich people are voting you, that means your overall vote count is better than everybody else. Okay, so in this democracy, not everyone is equal. Some are more equal than the others. Alright, meaning the people whose worth is higher than the other, they are counted, their votes are counted more. Alright, so it's a very straightforward join. Alright, here you can see that A voted C and B voted C, and C voted F and A voted B and F voted C. Okay, and the worth of A is 5, B is 1, C is 11, and the worth of D is 12. Alright, so the overall result is the total vote count of C is how much? A plus B and F, right? And which means A plus B is 6 and F has no worth right now. So we are assuming F's worth to be 0. Okay, so C becomes 5 plus 1, right? In the similar way, A is voted by nobody. You can see that A is voted by nobody. The vote count of A is 0 and vote count of B is 5 because B was voted by A and A's worth is 5, right? And C was voted by A and B, so vote count of C is 6. Alright, and about D was again voted by nobody, so D is 0 and E is 0. Alright, so right now we have this result here. So there could be many ways in this. If you are using SQL, you could have just joined list 1 and list 2, and then after joining we could have grouped by the voter and we could have summed up the values, right? We could have grouped by votee and summed up the vote count. So first we have to join the two tables and then we have to do the group by, right? That's what we would do if we do the SQL. And in case the second table called worth, if this table is very small, we could load it in the memory and then look it up. Look everyone's worth in this table and then get the results, right? Alright, so basically the idea is to join list 1 and list 2. Because if we try to load the list 2 into the memory or list 1 into the memory and try to look up, it will consume too much of memory and lookup might take a lot of time. Therefore, it would make more sense to join the two tables. And how do you join? You join by concatenating two files. Okay, let me show you. Alright, so when you give the folder as the input, the complete folder as the input to MapReduce process, all the files sitting in that folder gets concatenated. Okay, so how do you do that? This diagram is, let's say list 1 and list 2 are already tab separated, both of them, and we pass both of these list 1 and list 2 files to our job and they get concatenated by Hadoop. Okay, they get concatenated by Hadoop and in the reduce we get this. Okay, so when Hadoop concatenates it, it brings all the values of the key together. You can see that the key is A, which is the voter. Okay, if you group these two files, the two files on A, which is the voter, so key is basically both the sides, key is voter, therefore the worth and the votee will become together. Okay, so this is what we get in the reduce. So in reduce we get key as the voter and value as the worth of the voter and list of all the votees. Okay, so in the reduce in the reduce, we will generate next set of values. So if we concatenate the list 1 and list 2 and then do the map reduce, okay, such that this column is the key and this is the value. So all the values for each of these will come together. So for A, the values that will come together is 5, which is the worth, and B and C, who are the votees. Okay, these are the votees. Similarly for B, 1 and B, C, and so on. Right? So you get this full list. Okay, so now we have got in the values the people who got voted and how much they gained because of A's voting. A voted to B and C, and A's worth is 5. That's what it means. Okay? After we group based on the voter, this is what we get. Okay? After Hadoop brings all the values of the first column, which is key, this is what we get. So for B, the worth B's worth is 1 and B has voted to C. Okay, in other words, you could also say B contributed as one value to C, A contributed 5 values to B and C. Similarly, C contributed 11 to F, D contributed 12 to nobody. F contributed nothing to C. Okay, this is what it means. So in the reduce, we can generate the data saying that what is the value of each one because of the voting. So we could say B gained 5, C gained 5, A got 0. Although it's not necessary to put A0 because we want in the output A0 as the output in case nobody voted to A. That's why I'm putting one more column called A0. Alright, although it's not required. Similarly, C got 1, okay, and F got 11 here, and rest, okay, in the similar fashion for rest of the values. Alright, next is for rest of the values, also the same thing has happened. Alright, now we pass this data which contains people and their worth because of voting by different people. Why are we passing it through the Hadoop again? So that we could sum up the values for each key. Now, summing up value for each of the votee is very straightforward. All we have to do is make the first column as the key, second column as the value, and when the grouping happens, we will just aggregate as sum. So for B, 5 plus 0. For C, 5 plus 1 plus 0. For A, it's only 0. D is not there at all. And F is 11. Okay. So this is what we get as the result. Alright. So that was our voting problem. Alright. So although it might seem like the MapReduce, the whole paradigm is very generic and can solve all kinds of problems, okay, but there are few things you need to know. Okay, so if the job can be very well done by a single machine and you are happy with the time taken by it, okay, then you don't need MapReducer. Okay, you should not be using MapReducer just because you know it. It's not a design pattern. It's not a design pattern. It's not a best practice. It's a technique to solve heavyweight problems. It's a technique. It's a tool to solve the big data problems. Okay, if you're happy and you do not foresee data growing beyond what can be processed by a single machine, then you use your usual tools. Okay, because if you try to solve every problem with a MapReduce, you might get frustrated. It does not simplify the problem. Instead, it takes a reasonable amount of time to actually convert a problem into MapReduce. Okay. The second thing, the computation depends on previously computed values such as Fibonacci series. Okay. So what is Fibonacci? Let's say first mapper is computing 1, second mapper is computing a second term, and third mapper is computing third term. Now, second mapper will have to wait for the output of first one, and third one has to wait for the first two to finish, because it'll say that I'll sum up the values of the first two. Two is this. Okay. Therefore, problems like Fibonacci should not be attempted with the MapReduce. Okay. Now, third is that when you need real-time response. For real-time response, MapReduce is not a great solution. MapReduce has been designed to be fault tolerant. Okay. It is designed to attempt the same job multiple times and try to get it done somehow. One task tracker is down, no worries, let me try on second one, and so on. And that makes it very, MapReduce is very stable. As in stable, it gives you the result. It is resilient to node loss. But the same design, because of these assumptions, these purpose of being resilient and purpose of having it run on many nodes without having to overflow the memory. Okay, so that real-time response is cannot be expected out of MapReduce. Okay, so whenever you need real-time response, avoid using MapReduce in that case. Instead, use something else. Say, for example, you're building a search engine. So for indexing the web pages, MapReduce is a good phenomena, because for indexing the indexing the pages, in what does it mean by indexing the pages? So you have to download the pages from various websites, find out the keywords, and create a kind of index the way you see the index on the back of your book. Okay, so for crawling, MapReduce could be a great idea, indexing and crawling. But for handling the search queries, MapReduce cannot be used because it has an inherent latency. It has an inherent latency where it's assumed that we have sufficient time to launch our work. Okay. Fourth is, whenever you need the whenever your algorithm depends on a shared global state. What does it mean by shared global state? Okay, let's say all of the mappers need to talk to a central database. All of the mapper need to update a central database. Same row needs to be updated by many mappers. In those cases, what happens is the mappers have to wait for each other to modify or read from the shared state, and thereby the performance of individual mapper will be badly hurt because of shared state. So whenever the such situation arises where all the mappers are trying to talk to the same central server and waiting for the central server to respond, so what would happen is that for every record in your input data, there will be a trip to the central server, and the overall performance of your MapReduce process will be equal to the performance of the central server, because that's where most of the time will be spent, and thereby all of the mappers will perform really bad. Okay, so in these cases, whenever the algorithm, whether mapper or maybe reducers, they all depends on a central shared global state, you will be heavily cut down. Basically, when you cannot make a problem parallel, okay, only then you have the shared global state. And therefore in such situation, never use MapReduce. Okay, so overall idea is to break down your problem into independent set of problems and get it done parallelly. Get individual parts of the data solved parallelly on the cluster. Okay, and get it accumulated. All right, so in those cases it's good. Otherwise, if there is anything which is non-parallel, you will not be able to have good performance of the mapper reducer. Okay, all right, next is with respect to testing, keep these in mind. So always test your mapper reducer on small data, because there are all kinds of problems you will see. Second, and whenever you are testing on small data, always generate the data set using the random samples. Have 4 or 5 random samples ready and run your program against this random sample 2-3 times. Okay. Second is that separately test your mapper and reducer. The way I was testing in while I was showing you the streaming job, I was testing my mapper and reducer then and there before hooking it up into the Hadoop. Alright, so first separately test mapper and reducer. For example, we tested our streaming job using this kind of mechanism. Instead of directly giving it to Hadoop, I tested it offline by saying tail input file and then my mapper was pipelined and then sort was used and then reducer. And then we checked whether our mapper and reducer are working fine or not. In case of Java, which we'll cover now, in case of Java, we will be using MR unit. Okay. In case you are testing the predictions, and as with any predictions, it's very difficult to test the predictions given by any system. Okay. How would you test if somebody is telling you, giving you the current right advice? How would you test your advisor or anybody who tells you the future? How would you test them? Okay, the simple answer is you have certain data of the past for which you know the answers, for which you know the predictions. So you let the system do the predictions for which you know the actual answers and then compare his predictions with the actual answers. All right, that's how you generally test whether somebody is really a future teller or not. Okay. So you basically split the data into 2 parts, generally a sample set of 80-20, and the first 80% is used to generate predictions, while 20% is used for testing the predictions. All right, and then you basically compare the predictions against the previous, compare the deviation. All right, so that was testing. All right, one of the exercise is take all these 4 problems, try to write code them in your favorite language. Okay, create a project on GitHub with your code and mention no big data in the readme.md. Okay, so why do I want you to create a GitHub project? Okay, that's my question to you. So the reasoning behind creating a GitHub project is that today, in this today's world, when people look at your profile, when people are going through your profile, they generally look at your GitHub work. Okay, do you have any footprint on GitHub repository? It's okay if your code is dirty because it's better than nothing. If you do not have a presence on GitHub, it's considered that you are not very active. If you do not have presence on GitHub, people think that you are not very active technologically. All right. So it's important to have a project with a MapReduce code of yours on GitHub. Okay. This will give you visibility. All right. So if you go to github.com, you will know what to do. Okay. First, you go there and I mean sign up, register, and then create the project. And in the README, mention nobigdata.com. All right. And send me the link to your GitHub repository. All right, now the next problem. The problem is this one you have to solve and submit in the LMS. And all I'm looking for in most of these cases is, are you able to even write the pseudocode? I'm okay with the pseudocode in most of the problems, but it should be pseudocode. It should not be just a very high level description of the problem. Okay, it should be a pseudocode. Okay, so here the question is based on the content of a very large text archive, formulate the next word recommendation. For each word, prepare top 3 recommendations of the word. Okay, so you must have seen already that when you type a word in while chatting on the phone, the keyboard gives the recommendation of the next word based on what you have previously typed. Based on what you have just typed, it will give the next word recommendation. Right? If you type happy, it will immediately say birthday, or it will show you top 5 or top 3 recommendations. Okay? So how does it do that? Okay, the answer is quite simple. It has done it already. It has already pre-calculated it based on the historical information from Wikipedia. Okay, although it takes into account your chat history as well, but let's keep that aside. In general, it basically goes through the so in the back end, periodically it prepares the hash table, which contains the word and the next word suggestions, and so on. Okay, so you have to prepare this hash table. You have to prepare this file, or basically first and the next word suggestions list. Okay, based on a huge text archive. And how would you do that? You have to think about it. You have to find top 3 words that follow each word in the text. Okay, in case a word is in case some words are not following a particular word, you have to eliminate those. You just have to keep top 3 recommendations. All right, so think about it. How can you solve it in MapReduce? All right, okay, so let's move on to the next session. A quick question. Okay, so the data generated by mapper is given to the reducer and then it is sorted and shuffled. Yes or no? It's basically first given, the output is given to the mapper, and then the output of the mapper is first sorted and shuffled, and then the reducers are called. So the answer is no. All right. So the next question is now coming up. All right. The mapper can only generate a single key value pair for an input value. So, okay, let me ask you a different way. For input value, like we had lines, did our mapper generate only one pair of key value or multiple pairs of key value? So mapper can only generate single key value, true or false. The answer is false. Mapper can generate as many key values as it wants. Okay, as opposed to the traditional definition of map function. Map function comes from the procedural languages, functional languages rather. So map function comes from functional languages, and in the functional languages, traditionally map was supposed to translate one value into another. Okay, but here in case of MapReduce of Hadoop, mapper generates as many key value as it wants. Okay, if it wants to generate a million key values, it can iterate over 1 million number and then generate as many key value as it wants. Okay, it is not bound to generate only a single key value. Okay, moving on. This is again continuation with the previous question. A mapper always has to generate at least a single key value pair. Is it right or wrong? Is mapper bound to generate at least one key value pair? Can a mapper choose to not give the key value pair? Alright, the answer is wrong. Mapper is not bound to give out the key value pair. If it chooses, it will generate one. If it chooses, it will generate none key values. And if it wants, it can generate as many key values as possible. Okay, so mapper is completely free to generate as many key value as it wants. Even if it chooses not to generate any key value, Hadoop is completely okay with it. Okay, all right, next question coming up. By default, there is only one reducer in case of streaming job. Yes or no? How many reducer tasks are there by default? So by default there is a single reducer, but it can be split by specifying this particular command options called this. In case of Java MapReduce, number of reducers are decided dynamically, but I think this strategy had changed in recent versions. So in Java MapReduce also, I think by default it's one reducer. Okay. All right. I think this one is very clear. In Hadoop 1.0, what is the role of job tracker? So the job tracker delegates the MapReduce logic to task tracker. Okay, so the map logic is executed preferably on the nodes that have the required data. Yes or no? So the map logic is executed preferably on the nodes that have required data. Now, here is the little tongue twister. Question is, map logic is always is the keyword, executed on the nodes that have required data. What if the node that contains data is down? Will it say, no, I can't? If, let's say there is no task tracker on a node which contains data. Task trackers are down on the node that contains, on the data nodes that contain data. So will it say that, hey, I can't run your logic? Or will it execute by transferring the data on and elsewhere? The answer is wrong. It will transfer the data to the closest node, the nearby node, and try to execute the logic on the nearby node. Maybe another computer on the same rack, or maybe another computer in parallel racks. Now, next question. Where does Hadoop store the intermediate data, such as the output of map tasks? Output of the map tasks would be used in the reducer phase. So, where is the output stored? Is it kept in HDFS? Is it kept in local file system, or is it kept only in the memory? Keep in mind that we are talking about humongous data. So each task tracker might have, maybe, say there are two blocks on each task tracker. Each map task will be producing the output generated from two blocks, which is, say, 128 plus 128, say. So it will be 512 MB. So each map task, if it keeps everything in the memory, it is going to consume around 512 MB RAM. So do you think it makes sense to put it in the memory? So here we go. First, whatever mappers are spitting data, it's kept in the memory, and on the other side it's being saved onto the disk. So it's like a conveyor belt. Okay, so we call it a circular memory buffer. From one side we keep on throwing the data quickly, and the other side it's getting collected by the map task. Okay, it's like the conveyor belt when you receive your baggage on airport. On one side they keeps on putting your bags quickly, and then the conveyor belt keep on rotating and see that if it can be persisted, as in it can be handed over to the passenger. In the same way, the conveyor belt in analogy is a circular buffer. Okay, where on one end the map task will keep on writing to it, on other end it'll be getting stored in the disk. Okay, all right, so first what happens is that the mapper's output is kept in the memory quickly, so that map task does not have to wait for storage to finish. Okay, and then once map task has written to the memory, parallelly in another thread the same data will get stored in the disk. Okay, now this data is carried over to the reducer machine. It is not kept in the HDFS. All right, here is a little difficult question. Okay, so the whole of the HDFS block is available on a node and is fed to the mapper. Is it right or wrong? Is whole block fed to your map task? When I say whole, whole is in a very stricter sense. Every byte. So no, the input is split. Input is first loaded, is split using input splits, and part of which is transferred to the mappers. Now, this is what I'm going to cover now. All right, I'm going to go deep into this, and then then we will talk about rest of it. All right. All right, there we go. This is a very important aspect, and all of you need to pay a little attention to it because the same mechanism is also used by the upcoming technologies such as Spark, such as EC2, and similar systems. So the concept, even though the MapReduce per se is being kind of since it is not solving the real-time problems, so there are other alternatives to it, but this input split is something which we all need to understand clearly. Okay, and kind of a lot of magic goes in there. A lot of magic goes in there. Okay, all right, so let me answer that question about input split. So question was that on every data node, we store the data in the form of blocks. Okay, we cut the file ruthlessly. I mean, Hadoop or the HDFS cut the file ruthlessly, whether it's cutting the byte into two, okay, whether it's cutting the multi-byte character into two, okay. Say multi-byte character as in Unicode, a big character, say Urdu character, is generally represented in multiple bytes. Similarly, a Hindi character is generally represented using multiple bytes. So even if half of the character is on one block, half of the character is another block, HDFS does not care. HDFS will cut it ruthlessly. Now, does it mean that our word count will give the wrong results? Will the mapper, when we talked about mapper, we talked about it will get the data line by line. Every line will be fed to the mapper, and mapper will convert that into word count and give it out. Mapper will convert it into key value and give it out. Now, if the whole block is fed to one particular mapper, or the definition of line, right, may not be right, because half of the line will be one block, half of the line may be in another block, half of the character is in one block, and half of, if the boundary issues are there, okay, if there are boundary issues, you will see all kinds of problems, right? So something has to be done about it. Now, one strategy could have been that let's bring all the blocks together, combine them, and then convert them into line by line and solve the problem. But if we do that, if we combine all the files together and try to break it down into line by line, then the whole objective of splitting the data is gone, right? You have to transfer all this data to one node and then convert it into line by line and then feed it somewhere. That means the whole idea of taking the computing to the data is gone, because if you have to combine all these blocks to parse it and convert it to line by line, then it's the whole data has to be transferred, and thereby the purpose of mapper and reducer is completely lost. Correct? Therefore, it is done very cleverly. So the data is converted into something called input split in a very clever manner, such that only the data that is on the boundaries get transferred. Half of the line get transferred to the another, and so on. Okay. So on the lower side, you can see, let's imagine that this file contains 11 lines. So in this, what you see is there are 11 lines, and first 5 lines up to here is 128 MB. Okay, from here to here it's 128 MB. Okay, so the fifth line will be cut into two parts. Bigger part is in the left hand side and remaining part is in the second block from here to here. Again, the ninth line is, most of the part is in this block and remaining is here. So basically what I'm trying to show is in the lower part you see these are block boundaries. It shows that HDFS does not care about your lines. HDFS does not look into your files and try to guess its data type and what does it have. Why does it do so? Because HDFS is a file storage. It does not care about how you interpret the file. Same file can be interpreted as tab separated. Same file can be interpreted as let's say text by text or some other way. So the interpretation could be many for the same data, for which HDFS ideally should not care. All HDFS cares about how it's going to take care of the replication and all the strategy which we discussed earlier. Therefore, it cuts the lines into parts. It doesn't care because wherever the boundary is reached, it just slices the file there. And 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 I mean the HDFS command, the client, the driver, that is the one who does this slicing. But when we run MapReduce, we need to have each map task should have the full line. It should not be running on it should not be running on it should not be running on basically a single it should not be running on half word half line or something like that, because while we are talking to the data we need to have the complete line, otherwise our logic will be wrong, our output will be corrupted, our output will be completely wrong. Okay, so here this is a very important part. So what happens is this translation of the blocks into understandable data is done by something called input format. Input format converts your block into input split. This upper side is an input split. It's a finished version of it. This is what fed to the mapper. The translation from the block into split is done by input format, and this is what goes to. So you can see here. All right, let me try to see if I can capture the screen quickly. All right, you can see here. So you can see that the migration from this side to this side happens by a library called input format. This library, there are many libraries which handle different kind of input format. The one which we used by default without you knowing about it, the Hadoop streaming was using something called text input format, which basically interprets data line by line. The mapper will get the input as a single line. Single line means data is splitted by /n. Okay. Now the next question is, how does this translation happen? How does this clever translation happen? So I'll try to explain it. Let's say these are the three blocks. These are the three blocks existing on three machines. This is the first machine, this is the second machine, and this is the third machine. Okay, these are the three machines working on something parallelly. So the way it happens is, on the three machines, Okay, the input format will start on all the three machines in parallel. Okay, all the three machines in parallel. All right, so on all the three machines, the input format gets started with the input block. So on the first machine, it will it will be given the block, and it is supposed to convert it into input split. Okay, so what happens is, in case of first machine, it starts reading data from 0th byte and keep on, as soon as it encounters slash n, it will generate input split with the new line, and so on. It will generate a record. This is a record, this is a record, this is a record. So as soon as it reaches the record boundary, it generates a record. Meaning, in case of a text file, the record boundary is slash n. Okay, each input split contains many records. Okay, and so on. All right, similarly it will keep on going like this parallelly. In the same time, while the first one is moving, second one is also moving. Okay, now the second one, the way it starts is, it will keep skipping the data unless it encounters the record boundary. Same way on here, it will keep on skipping the data unless it encounters the record boundary. Okay, and this skipped data is transferred to the previous block, and that is the cleverness of input format. All right, so only this much data got transferred from third to second. Only this small data, this, you see the tiny little piece, only this small data got transferred from third to 2 and 2 to 1. And the other important part, that this reading of the data kept on happening on all the nodes parallelly. Okay, so the logic goes like this, that as soon as you keep on skipping the data, you keep on skipping the data unless you encounter a record boundary. The beginning of the file is also a record boundary, and thereby the first one does not skip anything. Instead start converting the record data into records. Okay, all right, let me try to explain a little bit more detail. All right, so Hadoop divides input into pieces called input splits. One mapper, one mapper instance is created per input split. Okay, split consists of many records, and map function runs on each record of input split. Imagine that in this diagram, the input split was somewhere here and here and here and here. Okay, let's say there was one line per input split. Therefore, there will be much more data transfer. If you have, say, 50 task trackers running parallelly on a single block, there will be too much of data transfer that happens. Okay, so while defining input split, you have to be careful. Okay, the ideal size of an input split is, it should be closer to the block size. Okay, so if you have very small input splits, there will be too many records and too much of overhead of transfer of the data. So good input split size tends to be equal to the HDFS block. Okay, so in our case where we did the word count, record means one single line, input split means some bunch of lines, and the input format was text input format. Alright, so a record in our case of word count was a line. This record could be very different for very different scenario. Whether you are handling an image, whether you are handling a video, the definition of record will vary a lot. Okay, so each input split is further divided into records. Okay, and every record, when we said our map function gets some input and does something, what it gets is one record at a time. The map function is applied on that record at a time. Okay? And a record is a logical entity. When you think about record, you used to think about a single row in the database. Okay? And the analogy, a single row, this is a very important one because everywhere, whether we are talking in R has an idea called data frame. Okay? Where it also has a record. So mostly when we deal with data, the idea of individual record is a very important one. If you are coming from database background, this record means a tuple. Okay, so the input format creates records and input format generates input split. All right, so there are many available input formats for you. The first default one is text input format. It converts the data, the raw data, into lines. Okay, it executes your map function against one line at a time. Okay, but Hadoop executes map function of a mapper one record at a time. Although while starting the process of mapper, the process will be instantiated only once for all the records. Otherwise, it will be too costly. If you are spawning a process, if you are creating a process for every record, then it is going to be too costly. So for every input split, only one process of mapper is created. All right. So let's say you are trying to deal with a file which contains /r instead of /n. In case of Windows, if the file is formatted using Windows, the the lines are the lines are separated by /r, not /n. Okay, so if you want to change that and you dealing with a file which is formatted in Windows, you might want to put different delimiter. Okay, you might want to say that my delimiter is /r. By setting this property, I'll come back to this one. If you have gone through the streaming API, there is a way of providing extra variables that you can provide here. All right, and when we cover Java, I'll show you this part. So while saying Hadoop jar this and that point of time, we can also specify what kind of text input format we want. Okay, what kind of input format we want, whether it's text or line input format. Similarly, we can send more parameters. All right, next is there are line input format. It splits, it makes sure that there are fixed number of lines in an input format, input split. Okay, so if you want number of lines to be same in all the input splits, then you can try to use line input format. Okay, so this text input format is a Java program. This line input format is a Java program. Similarly, there are other input splits such as fixed line input split format. Okay, whereby we say that our every record is a fixed length. Every record is a fixed length input form, fixed length. It's not separated by /n or new line. It's just fixed length. There are many fixed length formats, and most of the binary formats are actually fixed length. So you could use fixed length input format. Similarly, if you want to use, you have another input format available to us as key value input format. Okay, just as an example, let's say you are dealing with XML files. So if you search for XML input format, you see that. Okay, so you will find the XML. Okay, the XML input formats. So you can always locate XML input format, or let's say geospatial. Okay, so if you have a GIS file format, you can convert that into input format. Okay, input. All right, so there are many more input formats available to use in open source world. Okay, all right, so let's say your data is in the key value format, and key value format is not very old. Okay, so you could actually use key value format as well. Okay, next is that let's say you are reading a file format called sequence file. Sequence file is a binary format for storing the binary data, and most of the data gets is converted into sequence file before getting stored in HDFS, because sequence file is a very powerful format. Okay, I'll go into the details about these formats. All right, so the same data can be interpreted in many more ways. Okay, and for that interpretation, converting that raw data into some meaningful records requires translation, and that translation is done by input format. Okay, so that's pretty much for today, and we will continue this discussion on the next week. Okay, in the meantime, please submit the assignments, try to solve it. If you get stuck, give me a buzz, I'll try to help you. Okay, bye bye.